Today we have 3 speakers, as you know. The webinar is expected to last for an hour. We have 15 minutes for each presentation, for each speaker, and after that we have a short 5-minute round for questions. If you want to ask questions at the end of the presentation, you can use the raise the hand in the participants. You can find that option to raise the hand and ask a question to the speaker. Okay, so Vita, would you like to introduce the first speaker?
Yes, maybe just one more comment. If you could put your video off during the presentations, that would be great for the bandwidth, and maybe also mute yourself if you don't mind, so that the presentation goes fine. Yeah, and we are also recording it, as you know, and it's going to be probably, most probably even posted on the YouTube channel created by Vince for the CM SIG group. Okay, so our first speaker today is going to be Simone. Simone, maybe you could put your camera for a minute.
Yeah.
Yes.
Hello.
Hello. So Simone comes from University of Pisa in Italy, and he's going to make a presentation on antennas, for analysis of antennas using TCM for satellite antennas.
Okay. So first of all, thank you, Marta and Vita, for organizing this and for the kind introduction. And welcome everybody to the presentation that, has been said, deals with the use of characteristics mode analysis for the design of configurable antennas to be employed on nanosatellites. The other co-author of this work is Dr. Francesco Alessio Di Candia from, again, Pisa University. So this is the outline of my presentation. So first of all, I will give the motivation for this work, and then I show the model analysis for the considered platform, which is a 1-unit CubeSat. And then I'll describe the design of our proposed S-band, reconfigurable S-band antenna. And then I will illustrate the main results. And finally, I will draw some conclusion and ideas for future work. So small satellite have gained a lot of attention recently in the space industry, and especially picosatellite or nanosatellites such CubeSat has found a lot of interesting application. The basic unit, the single unit, is basically a cube of 10 centimeters of edge, and with a total weight lower than 1 kilo. But of course, we have 2 units, 6 units, and even more bigger kind of CubeSat. Of course, since the platform is very small, size and weight of the antennas are a critical factor, and especially also the stowing space if them to deploy antennas. And also the effect of the platform is really important, especially for, again, this kind of platform in which the physical size of the structure is comparable to the wavelength. And this is particularly true when we are considering UHF and S-band. So there are, of course, already solutions in the VHF and UHF band. There are deployable monopole or dipole. On the contrary, on the S-band, the most adopted solution is the microsweep patch or slot antenna, which, however, require some quite a not negligible footprint on the satellite face. So for the UHF and VHF case, we need the deployable structure. S-band, this is not required, but we have some footprint that we need to occupy on the platform. And among the proposed solution, very few are able to switch between linear and circular polarization, and even fewer are able to provide pattern reconfigurability, which is often achieved by using multiple patch antennas on the same face. So this requires, again, a large area. And sometimes also the analysis of the platform effect is done a posteriori, So this requires additional investigation. So we believe that characteristics mode analysis can be helpful in designing antennas for this kind of application. Since I think we are all quite aware of the basic theory, I will skip this basic relation that we know very well. But here the main point is we need, our aim is to find the proper kind of exciters and also the position of these exciters in order to achieve a very small compact radiating system, which can provide, again, pattern reconfigurability. So we need also to pay attention, of course, also at the magnitude and phase that we use to feed the exciters. So basically, we know already that there are two kinds of exciter. The capacitive exciter one, we need to put on the minimum of the related current distribution, and the inductive coupling exciter, which have to place on the maximum of the related current modal distribution. So we can have a half loop in this case, or small slot on the platform. So we have some previous experience on applying characteristics mode theory on three-dimensional platform. And as a result of this work, we have seen that we have found these balanced inductive exciters, which can generate the same current of the, let's say, standard half loop. But what we have found out is that using the balanced inductive exciters, we are able to achieve, let's say, a higher purity in exciting a single mode. So when we want to excite a single mode, we can excite only that one and not some also other undesired mode. So this is just a comparison between the standard half loop exciters and what we can achieve with this balanced inductive exciter. So we can really be quite selective in the excitation of the field. And the reason of try to achieve this purity excitation is that if we are able to not lose power, let's say, in other unwanted modes, we can have an higher radiation efficiency. So then if you want additional details on this, you can give a look to this publication. So we think that this new kind of exciter could be helpful in designing a small and low weight antenna for the CubeSat. Of course, we cannot cut the platform or make big changes. We need to be really minimal invasive. So we started by considering a simple model for the CubeSat, just a cube. And then, of course, we have performed the characteristics mode analysis. And as you can see, there are several degenerated modes because this is due to the high level of symmetry, of course, of the platform. But and then we are addressing the S band, so we are working within this frequency range. So the current and pattern I will show are in the middle of this band, but we can reasonably agree that this behavior is the same in this band in terms of radiation pattern and current. So the idea is, again, considering the modes with model significance higher than 0.7, as we always do. And then again, the aim is to find the proper place for the exciters and be, again, minimally invasive. So first of all, of course, we need to look at the current distribution that the platform can support. And again, here you can recognize that due to the symmetry, the current distribution can be similar. It depends on only which phase you are considering. But then, of course, since we need to we want to achieve pattern reconfigurability, we need to excite more than one mode, and of course also to pay attention to the radiation pattern associated to each modal current. So we performed, first of all, we decided to place the exciters along the borders. So in order to save space and to not interfere with solar panel or other platform or payload, for example, cameras that can be placed in the middle of the phase. And also we want to exploit only one phase. These were the hypotheses that we did since the beginning. And of course, our exciters has to be small enough, also because these CubeSat are put together inside a single launcher. So they are piled up, so we don't have, also for that reason, to use a lot of space. So for this reason, we decided to try to employ these balanced inductive exciters, since they are quite small, be placed on the edges, and of course of the maximum of the current distribution. So if we look to the model weighting coefficient, we can draw some interesting conclusion. We can excite several modes. For example, if we use the port 1 and 2 together with port 3 and 4, we can stimulate mode number 1 and mode number 2, mode number 5, 6, which are degenerates, and also mode number 10, because these, with the proper phasing, we can excite those modes. And then if we use, for example, only the couple of port 1 and port 2, again, with proper phasing, we can excite mode 4, 9, and 12. And similar things, mode 3, 8, and 11. And then if we use port 3 and 4, we can excite mode 4, 9, and 12. Not surprisingly, we cannot excite mode 7 with this particular displacement of the exciters, because if we look to the current distribution, there is no maximum here on the edges and also in the top face, so we are not able to excite this mode. But I think we have, we thought we had enough with these 4 exciters. And so again, we're considering the center band, but we can extend it as a result to the entire bandwidth from 2.4 to up to 2.45. And so, of course, we have to check the radiation pattern corresponding to each mode. And we have a pretty nice variety, because we have a radiation pattern with the maximum at the board site, but also with some null. So we can mix, let's say, these different radiation pattern in order to achieve a nice reconfigurability of the radiation pattern. So in the end, the first thing we did is to find the proper feeding of this balanced inductive exciter in order to achieve a circular polarized signal in broadside. So all the single ports are quite matched. This is an anticipation, so this is the comparison between the measurement and simulation of the axial ratio, which is quite good. The maximum gaze is higher than 6 dBi, and here you can see some colored map again when we are pointing broadside. So each port has this feeding. Then, of course, we realized this homemade CubeSat mockup, and I want to stress that due to the employment of these exciters, we have a great saving of the required volume compared again to the solution with patch antennas. And also a lighter solution, because patch antennas, of course, require the electric substrate. And again, we decided to exploit only the top face, but of course we can use also other faces as well. And then, of course, you need some feeding line beneath this top face, and everything so boils down to a single microstrip line. And another very important thing, we are able, as we show, to steer the beam by only controlling the phase and not the amplitude of each feeding port. So this is also very good in terms of efficiency. And so these are the final, some example of the final results. So we optimized the phase of each exciter in order to simultaneously stimulate the proper modes. And then here, for example, we are pointing at the direction theta 30 and phi 30. And here, this is an overall map which describes with a yellow area when the axial ratio is less than 3 dB, and the gain is only 1 dB less than the maximum. And then the green is when, again, the axial ratio is acceptable, but the gain is between 1 dB or 3 dB less than the maximum. And then the blue one when the axial ratio is not acceptable anymore. But so in this case, we are able to steer a circularly polarized field, which is quite a unique feature so far. And then this is just another example with theta equal to 10 and phi equal to 15. So we are pretty able to scan the beam up to, let's say, 40, 45 degrees on a theta angle, getting acceptable acceleration and of course the gain. So here I'm just showing some cuts of this plot, but basically this map is kind of summarizing pretty much everything. And then we are also able, of course, to achieve a linear polarized field, again, by properly feeding with the proper phase each exciter. The gain is something greater than 5.5 dBi, and we can scan up to, let's say, 55 again degrees in theta. So I don't know how much time do we have, but I'm going to the conclusion. So we think that this is a really interesting topic, and that the small satellite domain will be more and more important for application, for example, for industrial Internet of Things, or for machine-to-machine communication. Also, there are some ideas of using, again, the GSM or LoRa bandwidth. So there is a lot of idea on this topic. And so I think in the end, what we proved with this work is that characteristics mode analysis can really help in find a really effective new solution for a small satellite, especially good in terms of low profile and lightweight. This particular solution, I think, is also the one, I mean, to my knowledge, that is able to steer the beam with circular polarization agility. Another very important thing is that we do not require any deployment of the antenna, which may sometimes cause the failure of emission. And also, it is intrinsically in the characteristics mode analysis that we take automatically into account the effect of the platform. Actually, we are really exploiting it. And now we are currently, of course, working for antennas to be placed on 3U, 6U, and 12 unit, and also to find a way to use multiple beams to get extra degrees of freedom for the designer and for the data link. And so that's all. And thank you for your attention.
Thank you, Simone, for this presentation. I would suggest, if you have got any questions, to raise your hands, and we can proceed to the question and answering part of this presentation.
No question?
I was too clear.
Hasanen, go ahead.
Yes. Hi, everyone. I've been handling another call at the same time, so probably I missed something. So my question, the first question is about model weighting coefficient. So you've shown graphs of the model weighting coefficients maximized to 1, kind of normalized. So yeah, the model weighting coefficient depends on the excitation, which is a voltage or a current or whatever it is. How do you normalize this?
Sorry, I don't know. There was this host has asked to start your video. Yes, start my video. Okay. Sorry, I will try to share again the presentation so we can. Can you see my screen?
Yes, we can.
Yes.
Okay. So maybe you are referring to this. So here I was just summarizing which. So by feeding, let's say, port 1 and port 2, how much I'm able to excite each single mode, and then the same by exciting port 3 and 4, how much I can excite each single mode. And then, of course, if I want to excite properly a single mode, I need also to provide the, let's say, proper phasing. So, for example, as I was showing here we need to give the proper phasing, for example, for achieving right-hand or left-hand circular polarization. So it depends. You need also to provide the proper phasing. So here I was not showing which phases I was providing, but this is just an example to achieve the broadside CP radiation and the proper phasing.
Yeah, I mean, in terms of calculation, when you go to calculate the mode weighting coefficient, if you show the equation, for example, that you had on the second slide, I believe.
Yeah, but so here I'm feeding port 1 and 2, and I'm using FICO to evaluate the model weighting coefficient.
Okay. So why the maximum is 1 is normalized. In FICO, I do remember that.
Yeah, I normalized this to the maximum.
Which maximum, of the voltage or the maximum of the model weighting coefficients?
The maximum of the model weighting coefficient.
Okay, okay, thank you. So, but I mean, there might be some further discussion about this. Probably we can have it later. I have another more general question. By the end of the day, this is a product, right? And you're trying to use the chassis of the satellite to feed, to generate currents that generate some radiation patterns.
Yeah.
And we know that on a satellite, there is not only one single radio, there is various systems, different frequencies. And sometimes you don't have EIRP limitations, so you go high in power. So what have you even been considering if you are exciting further modes or further radiation patterns at different frequency that can cause some interference with other systems? How you would solve this if you have the characteristic modes approach?
So thanks for the question. So first of all, I did myself the same question, but we have also to realize that even if we put a patch antenna like the standard commercial one, still we are exciting current on the chassis. So all solutions at different degrees have same problem that you were raising. So there could be some, let's say, compatibility, electromagnetic compatibility issues, but I think this is the same for also is a problem also of other solutions. The thing I want to stress is that here we are really exploiting a single phase. So what happens on the other phases is not really very important for the current distribution than for the radiation pattern. Of course, we need to pay attention to possible interference, which again can happen also with other kind of antennas. And currently we are also checking what happens, for example, if we have solar panel or if we have a camera, because of course the model current distribution is a little bit changing on that phase, but we can work around this and then again, the analysis since the beginning, if we know that there is a camera, and then excite the proper modes to get again the pattern reconfigurability. So of course, we need to make a dedicated analysis if we have a different platform. So for example, if I go to 2 unit, 6U or 12U, I need to, I can follow with the same approach, but I need to redesign it again because I cannot just place, these exciters on the edge. So you're right, but.
Yeah, and plus you have the enormous advantage that you have access to 4 phase groups, basically, that you can cancel the pattern or create nulls in some direction if they are causing problems. That's basically something that we do with 5G, for example. We place a null on the interference source. So I think because you have this flexibility, you have access to 4 phase groups or a group of 4 phases. So you can also have this on your side as well. Thank you.
Thank you.
Are there any more questions from anybody else? Okay, maybe. Thank you, and thank you again, Simone, for the presentation, and thanks to you, Hassan, and also for the questions. I'll let Marta introduce probably the second speaker.
Okay, our second speaker is Peter Futter. He represents Altair company. They develop FECO software. And he's going to present the work antenna positioning for bandwidth optimization using characteristic modes analysis. Okay, Peter.
Yeah, thank you very much. Today I'm going to be talking about antenna positioning for bandwidth optimization using characteristic mode analysis. And just a bit of background before we get started. So last year we presented a design for an LTE low band antenna for tablet using characteristic mode analysis. And while the design worked rather well, we did not really manage to sort of generalize the approach that we followed to achieve that design. So it kind of felt like there were still some questions around. And that was really the motivation for the work that we started for this submission. And the goal really then was to develop a positioning strategy, obviously using CMA, but for a single antenna, and focusing on antennas that have wider band characteristics. And once again, the focus of this work was predominantly more for mobile or wireless applications. So I'm going to start off with a brief summary of the approach that we followed. Then the method was basically starting off from a well-defined or well-understood reference, and then extending our designs to wider bands, reducing to single transmitters, and at that point kind of deriving a methodology, and finally applying that method to two further examples. So as far as the simulation approach was concerned, we wanted to start from a well-understood reference, and from there make incremental changes with respect to different antenna types, changing frequencies, different antenna positions, and also throughout the whole study, we used the same ground plane size to have some sort of consistency through there. CMA was used predominantly working with the modal weighting coefficients and obviously the modal current distributions as well. So I mentioned the focus being on wireless devices. We therefore worked in typical frequencies, so between 1 and 2 gigahertz, and also relevant ground plane sizes of a modern smartphone today. And the primary objective was really to focus on antenna bandwidth. As far as the simulations were concerned, the simulations were run with FECO, and some of the designs that I will show were matched using OpteniLab. Okay, so as a starting point, we just implemented a standard modal excitation configuration. Here you can see an inductive coupled element used to excite mode 1 in the upper graph and mode 2 in the lower graph by placing the elements in both cases at the modal maximum in the modal current distribution. So there are two or three things you'll notice here. Firstly, we are able, as the strategy suggests, we are able to excite the mode that we intend to excite following this approach. We do, however, also in both cases excite an unintentional mode. So in this case, it's mode 7, and in the lower case, mode 6. If we look at the modal current distribution, you'll notice that the unintentional mode in both cases does have the same attributes as the mode that we are trying to excite. Then also just do note, in this case, we implement this over, so the radiating element here, or the antenna, is very, very narrow band. It's matched with a tuning capacitor, and that gives us about a 5% bandwidth in this case. In the next step, we've moved to using an antenna with a larger bandwidth. So in this case, 4 patch antennas, again, following a similar positioning strategy. However, in this case, we are working with capacitive elements. So to excite the long mode, we place the elements towards the null in the modal current distribution, and also have a 180-degree phase shift between the upper and lower elements. What you'll notice here is, once again, we are able to excite, in this case it's mode 2, which is the long mode as intended, but we do also excite an unintended mode, and in this case actually slightly better than the mode that we intended to excite. But with respect to bandwidth, we are able to excite both of these modes over the full 30% bandwidth in this case. Maybe also just to point out, since it was a question after the previous presentation, so I personally like to work with the modal weighting coefficient in dBs, just because often you're working in sort of a relative manner. You want to know one mode versus the other mode, and it just gives you a bit more range when you're working with the smaller values. So the third case here is a printed inverted F antenna, and we're showing 3 different positions because it gives some insight into the correlation between the modal weighting coefficient and the bandwidth. So if we start with the center-fed case, in this case that's the green result here, this design excites mode 1 very well. If you were to look at the S parameters, you would see a very deep null, but this correlates to a rather small bandwidth in this case. And then we move to the nominal position, or finally to the corner position. You'll notice that there's sort of a spreading of the modal weighting coefficient, and this has a very strong correlation to the bandwidth that we see for these cases. So for the corner case, where we have the largest bandwidth, we are able to excite mode 1 almost over the full bandwidth of the antenna, and there's a small contribution of, in this case, mode 5 in the upper band. So the next step then is to start reducing to a single antenna. And the results that I'm showing here, so we're going to use some of the same antennas, but comparing, for example, here the modal weighting coefficient of this case with the single antenna to the previous case where we had 2 antennas. So those are the results in black. Immediately what you'll see here is, as with the case with 2 antennas, we are able to excite, in this case, mode 2. Not quite as well as when we have 2 antennas. However, what we do see is that we previously we had 1 unintentional mode, where now we have 3 unintentional modes. And where things are interesting here is, if we look at the bandwidth and compare that to the previous case with 2 antennas, the bandwidth is the same. So there seems to be at this point some correlation between having more modes and bandwidth. The same can also be seen if we look at the long edge case with the slot antenna again. So previously we had these 2 modes. There's a bit of a shift in frequency, and we also now have 2 additional modes in this case that are excited. The condition for the patch antenna example that we looked at previously is a little bit more pronounced. Reason being twofold. Firstly, we are reducing from 4 antennas to 1 antenna. And the other influence here is that this design is at 2 gigahertz. So for the ground plane at this size, we have more resonant modes that occur at the higher frequency. So what we see effectively when we reduce the number of transmitters is, firstly, there are once again more modes that are excited, but the behavior is a bit different. We see kind of a sub-out of resonance throughout the band. But once again, despite quite big differences in this aspect, in the modal weighting coefficient, the bandwidth remains unchanged here. So if we want to start to deduce some findings at this point, reducing to a single antenna seems to be kind of equivalent to relaxing the boundary conditions for the modal current. And it basically means it's easier, so by having less antennas, it's easier to excite non-symmetric modes, which may or may not be detrimental from a larger perspective, but with respect to bandwidth, so far these unintentional modes still seem to contribute positively to the overall bandwidth of the antenna. So at this point, we tried to derive kind of an approach with respect to a single antenna positioning using CMA. So the first step seemed to be important, obviously, to have an understanding of the kind or the characteristics of the antenna that you want to use. In other words, is it or does it exhibit inductive coupling or capacitive coupling behavior? The next step would be to decide which modes to excite. And there are probably 2 points to mention here. In general, or typically, you may say it is easier to excite modes with a higher modal significance. But in the context of this work where bandwidth is our criteria, it's also worth looking at kind of the bandwidth properties of the modal significance. In other words, it may be beneficial to excite a mode that has wider band properties rather than a mode that has a higher modal significance. So then, based on our positioning strategy, we know that for inductive elements, we place these at the modal current maxima, and conversely for capacitive elements, we place these at the current minimum. And what we expect to happen then is we will excite the intended mode. However, at the same time, we expect to excite these unintended modes. And as we've seen, there doesn't seem to be a degradation in the bandwidth behavior when we excite these unintended modes. So at that point, we can perform our CMA analysis and verify what we've achieved from the modal weighting coefficient and also having a look at the modal currents. So the next step then was to take this approach and apply this to 2 different examples. So the first example we looked at was again the PIFA antenna. So here now, obviously using a single antenna, we know the characteristics of the antenna and already that the best positioning for exciting mode 1 is on that corner position. So now we're going to follow that same strategy with a single antenna. So as previously we had mode 1 and 2, we now have, in this case, 4 additional modes that have a modal weighting coefficient above -25 dB. And the graphs that I'm showing, or the modal current, the current distributions that I'm showing here are the synthesized currents. So FECO offers a macro that allows us to combine or sum the modal currents. So what I do is at this frequency in 840 megahertz, I've added the 3 modes here, and they're weighted by the modal weighting coefficients. So this is kind of like the synthesis of the total current that we can expect. At 1 gigahertz, there are a couple more modes that come to play. So we sum mode 1 to 4. And at 1.16 gigahertz, we have all 5 or 6 modes that we sum. So you'll see at the lower frequency, we have kind of the properties of mode 1, where this is what we expect because it has the largest amplitude. As we go up in frequency, this becomes a bit more distorted, but we still have some characteristics there. Then, just as a form of verification, we ran a traditional optimization there. You can see some S parameters plotted at various points here, with our optimum being on the corner, clearly indicating the highest bandwidth. And also on the right, you can see the output of the optimization goal as a function of dy. So it's basically maximum on the corner, dips off somewhere towards the middle, and then raises a bit again towards the end. I don't think I have enough time to go into this slide, but please feel free to read the publication, just noting that we used a different definition to optimize S11, or in this case, bandwidth using S11. So the final example here, we used the antenna that we designed for the previous EU CAP in 2019 and applied the same approach with positioning. So two things here of interest. Firstly, it's a capacitive element, and the antenna design is inherently multi-mode throughout the operational bandwidth. So a little bit more complex with respect to its behavior. But once again, the result is consistent with our other examples. So we see multiple modes are excited, with mode 1 being the intended mode, and these other modes, again, as we go up in frequency, more modes being resonant. And again, we can perform our modal current synthesis to show kind of the expected behavior throughout the bands there. Once again, we performed an optimization just to verify. You'll see the maximum is slightly offset from the edge, and that is just to do with the flange that runs around the side of the antenna that connects this sort of radiating element that runs along the top of the slot. So finally, the conclusions for the study. So firstly, I think it's clear to say if your goal is to achieve a pure modal excitation, the best strategy that you can follow is using multiple antennas, preferably over a narrow frequency band, and then depending on the application and the specifics, you may be able to isolate a single mode, or you may have one or two unintended modes that you excite. However, obviously for many applications, this may not be practical. You may be limited to a single antenna or may have a requirement for a broader band. And then the approach that we investigated here comes into play. And the conclusion with respect to that is that although reducing to a single antenna and even working over wider bandwidths will result in sort of unintended modes being excited, primarily with respect to bandwidth, these modes do seem to contribute positively to the overall bandwidth in that regard. So based on these findings, we developed an approach with respect to working with a single antenna, following the placement with respect to bandwidth, and then went on to apply this to two different antenna examples where we used traditional optimization as a form of verification to the maximum bandwidth. Thank you very much for listening, and I'm happy to answer any questions if there are.
Okay, thank you, Peter, for the presentation. I think we have time for a couple of questions. No question?
Can I say something? I don't know how to raise the hand.
Okay, you can
okay, thank you for a very nice presentation. Maybe I missed the point. So is there a way to foresee the best position for exciting, these multiple modes, or you have necessarily to perform the optimization you were showing? Maybe I missed that point.
So the strategy is very, maybe I can share my screen again. Essentially the same as a sort of standard approach where you work with multiple transmitters. Sorry, there we go. Basically, the approach is depending on the antenna type, if it's capacitive or inductive, you will place that element either at the modal current maxima for the mode that you are trying to excite, or for an inductive element, or for a capacitive element, you place that at the modal current minima. And what you will get with that is you will excite the mode that you are trying to excite. However, there will be other modes that are excited.
Yeah, but I was thinking, since then you are using less exciters than, let's say, the number that is required to purely excite the mode. And then you were showing that you were moving at some point the position of the exciter to get, I mean, the widest possible band. So I was wondering if this parametric is really necessary, and then you optimize the actual one as you show, or if there is a way to exploit the characteristics analysis in order to avoid this.
Sorry, maybe I wasn't clear enough yet. So we used, so I think this is one of the slides that you're referring to. So we just used optimization as a form of verifying the approach. So here the result confirms that the optimum bandwidth or maximum bandwidth is at the location that we placed the antenna using the CMA approach.
Okay, thank you.
Yeah.
Okay. We have another question, yes. Kapil?
I have a question. Somewhere you mentioned that you combined the modal currents, different modal currents to visualize the dominated current. Are you considering the weighting coefficient as well, or you just only consider the modal currents? Yeah, in this place. So like, yeah, you consider the modal weighting coefficient along with the combined modal current or not?
Yes, so the macro that I used for this has two different modes. This mode is it's called the synthesis mode, where it just basically uses the modal weighting coefficient when it sums the currents. The other mode is a more design mode, and there you could actually use different weighting if you want to tweak the weighting, basically. But here,
yeah, another question is there any relation with dominated models or modal weighting coefficient when we correlate with the combined modal currents?
So I think here you can see that probably most nicely in this image. So in this case, we have, what's that, a couple of dBs, probably 5 dBs separation between mode 1 and mode 2 in the modal weighting coefficient. And the properties in this case are sort of arguably dominantly mode 1. So there is some properties from mode 2, but the dominant mode is mode 1 in that case.
Thank you.
Okay.
I have one question.
Okay, go on.
So here I want to know the capacitor that you used. I want to know what is the effect of the capacitor on the characteristic modes, and did you try to change the value of the capacitor and see if it has, like, the value has even effects?
It definitely does have an effect. I ran these simulations a very long time ago, so I'm not going to be able to give you an exact answer to what it does, but I can tell you the approach that I followed. And that was, I wanted my resonance to be centered at 1 gigahertz.
Yes.
So I set the capacitor value for this antenna to have that behavior, and this is the result that you get. So I think, you know, if you wanted to do a design here, you may need to consider the size of the antenna in this case with the value of the capacitor, because the combination of those two parameters will change the modal behavior. Yes. Yeah.
Thank you.
Okay, if there is no more questions, I think we can move to the next speaker, the last one. Evita, would you like to introduce her?
So our last speaker, the last speaker of this webinar is going to be Nadia Kari. So Nadia Kari comes from France, from the Universite Gustave. She's actually my PhD student, and she's now working in the second year. She's now in the second year of her PhD. So her presentation is her talk is going to be about circularly polarized, electrically small antennas, and based on chiral metamaterials.
Yes, yeah, okay. So, hi everyone. So today I'm going to present my work, circularly polarized electrically small antenna using chiral metamaterial and based on characteristic mode theory. So with the development of wireless communication system, electrically small antenna become a topic of intensive research due to their compact form and potential use in various wireless applications. On the other hand, some applications require circular polarization radiation in order to avoid polarization mismatch. For instance, for a 5G wireless communication system or for biomedical application and so on. So here's some method. Mainly, we have 4 methods to achieve electrically small antenna with circular polarization. The first one is based on the use of helical antenna. So it was demonstrated that helical antenna can achieve CP radiation. CP radiation. Okay, so the use of helical antenna, it was demonstrated that the use of ring antenna can achieve CP radiation. The second one is based on the use of 2 orthogonal linearly polarized radiator with quadrative, in phase of 90 degrees. And the other method is based on combining 2 signal feed chiral particles to achieve a CP antenna. The main issue with this method is that based on empirical approach and the matching to 50 ohm, it's not straightforward task. On the other hand, we have another method which is based on the use of chiral metamaterial to achieve ECP antenna. And in this contribution, we adopt this method. Why? First of all, we know that electrically small antenna are not good radiators because they have low radiation resistance and high reactance. So many research have focused on the use of metamaterials. As a brief definition, metamaterial is can be defined as engineered metamaterial characterized by their unique ability to handle electromagnetic waves and to enhance electrically small antenna performances. So when we combine these metamaterials as parasitic elements with dipole in the near field region, we can have energy compensation and kind of enhancement, and this leads to the concept of metamaterial inspired antenna. However, the classical metamaterial cannot lead to circular polarization. So we have in literature there is a particular metamaterial which is chiral metamaterial. This chiral metamaterial can be defined to the geometry that cannot lead to their mirror image and have no symmetry plane. And one of the most important characteristics of this chiral metamaterial, it's the asymmetric transmission, which leads to circular polarization. And of course, it enhance the electrically small antenna performance. So by associating this chiral metamaterial to antenna, we can achieve ECP radiation, electrically small antenna with ECP radiation. In general, This association is based on heuristic association. So this leads to our objective, which is how to propose a systematic methodology to achieve a circularly polarized electrically small antenna using chiral metamaterial. So we will study in this contribution, we propose to study electrically small dipoles with the chiral metamaterial, and we try to understand the energy compensation in the near field between the small antenna and the chiral metamaterial. So to better understand and to better associate this chiral metamaterial to electrically small antenna, we propose to study it with model analysis, since model analysis brings to us a full physical insight in phenomena radiation, and it allows us to better understand the behavior of this electrically small antenna. So an important question could be asked here: how to associate? So to associate, thanks to CMA, we can differentiate between the metamaterial, the type of metamaterial, if it is electric or magnetic. So first of all, we need to analyze the metamaterial, and using CMA, of course. And on the near field region, we will analyze the behavior of this inclusion. So here in this inset, we have, we have the workflow of how to obtain, how to associate, how to classify, the metamaterial to electric or magnetic metamaterial. So first of all, we need to calculate the impedance matrix, and after we need to solve the linear system. And after solving this linear system, we obtain the eigenvalues. So based on the eigenvalues and the sign of the eigenvalues, we can classify our inclusion as electric or magnetic. So if we have eigenvalues equal 0, so this inclusion is resonating at a given frequency. And if the eigenvalues is negative, so we can classify at a given frequency that this inclusion is electric, or it's a magnetic if it's positive eigenvalues. So the geometry is considered as a magnetic, the mode is considered as magnetic mode. So I would like here to introduce two main metrics that allows us to better understand and to better apply this this methodology. So first of all, the moderating coefficient, it represents and describes the response of the mode under an external excitation. And the higher the magnitude of this coefficient, the more important role plays on the radiation of the antenna. And and I would like to note that here the moderating coefficient is not that we will present after. It's not normalized. And the other one, the intermodal coupling. So it represents the relation between modes inside the structure. So here I would like to propose the methodology used to achieve a CP antenna, electrically small antenna with CP radiation. So first of all, we will analyze the chiral metamaterial separately, and after the antenna separately. So first of all, using CMA, we will solve the metrics given by CMA, eigenvalues and moderating coefficient. For the eigenvalues, we interest just for the first three modes, to check the resonance and to have an idea about the first three modes, if it's magnetic or electric mode. And after, for the moderating coefficient, we will use this metric to have an idea how to excite the antenna and how to obtain CP radiation and the position and the direction of how to excite the chiral metamaterial. On the other hand, the antenna alone, I would like to mention that this antenna that we will use, it's not resonating antenna. So for the metrics given, we interest just on the eigenvalues. So we can know that the first three modes, if they are electric or magnetic mode. And after this, after analyzing the moderating coefficient, we can combine this antenna to the chiral metamaterial, and we can have, after analyzing, of course, the moderating coefficient and knowing the best position and the direction of how to excite this chiral metamaterial, we can place the antenna to to the chiral metamaterial. And after using CMA, we will try to understand this coupling between the antenna and the chiral metamaterial, checking the resonance, the antenna performance, and also the intermodal coupling. So now let's move to this application, how to apply this methodology and how to obtain SFP radiation. So first of all, as I mentioned, we will analyze it separately. The double turn helix, it consists in two turn helix of perfect electric conductor. The resonating frequency is 2.8 gigahertz. The overall size, it's lambda over 15 by lambda over 39. And it's resonating at 2.8 gigahertz. On the other hand, we have a small dipole, which is non-resonating, and it's a perfect electric conductor, and non-resonating at 2.8 gigahertz. So here, the results given by CMA of the chiral helix only. So we represent here the first three modes. The mode 1, it's resonating. So it goes from electric to magnetic energy, and we have resonance at 245 gigahertz. The second mode and the third mode, they are non-resonating mode. So here we have the current distribution of mode 1 and mode 2 and mode 3, and this current are normalized to the maximum. So to better understand how to excite the structure, now we propose to study 6 different configurations of virtual excitation, virtual dipole, magnetic and electric, in the direction of X, Y, and Z for both a magnetic virtual dipole and electric virtual dipole. Okay, so here the results of the moderating coefficient of the 6 configuration. As we can see, the most important, the higher moderating coefficient in the direction of HX. So the magnetic field is excited in this direction towards the axis of the helix. So and after we have the configuration HY and HZ, but the highest response and the best response is when the magnetic dipole is placed in the HX position. Now we will move to analyze separately the antenna to better understand the behavior of this antenna. Of course, it's non-resonating. So the overall size of this antenna is lambda over 39. At this frequency band, the antenna is non-resonating. We have mode 1, which is electric mode, and here the current distribution, it's like regular dipole, small dipole. And the second one is electric mode, sorry, it's electric mode, and we have the current distribution here. It's normalized. And the third mode, it's a magnetic mode. And here the current distribution, which represent like a loop antenna. Now let's move, after analyzing the moderating coefficient and knowing the best position, how to excite this chiral metamaterial to obtain the best position and the best excitation. We will study the combination and try to understand how the energy compensation between the dipole and the chiral metamaterial. So here the eigenvalues of the proposed antenna, which is resonating at 2.4 gigahertz. And mode 2 and mode 3 are non-resonating, and they are electric mode. Here the current distribution of mode 1, mode 2, and mode 3. And the current distribution is also here normalized. So we have only mode 1 is resonating, and we have resonance before the dominant, the resonant frequency of the chiral helix alone. So the chiral helix is resonating at 2.45 gigahertz. Here it's resonating at 2.4 gigahertz. To better understand the energy compensation between the dipole and the chiral helix, so we propose to study the intermodal coupling, the reaction between the modes. So here, the intermodal coupling in the left of the first 4 mode. So as we can see, the higher values are of mode 1 and mode 4, and the other mode are neglected almost. So here the current distribution of mode 1 and mode 4 of the proposed antenna to better understand the behavior and the coupling and the energy compensation between the dipole and the chiral metamaterial, we propose to check the current distribution, the characteristic current distribution. So here this is for mode 1 and here for mode 4. So we propose to check the different mode of the helix alone and the dipole alone. As we can see, we have mode 1, which is similar to mode 1 of the proposed antenna, and we have here mode 3 of the dipole, which is similar to mode 4 of the proposed antenna, and we can conclude that, we have similarity between mode 3 of the dipole alone to mode 4 of the chiral of the proposed antenna, and mode 1 similar to mode 1 of the proposed antenna. So we can understand that there is compensation between mode 3 of the dipole and the first mode of the chiral metamaterial. Here we pass to antenna performances. So using full wave simulation, we study the antenna performances. So here the S parameter. It's resonating at almost 235 gigahertz. We have an axial ratio at phi equals 0 and theta equal 110 degree, less than 3 dB. And here the gain at 0 degree and 110 degree. So as conclusion, we propose this contribution is a systematic methodology to design a circular polarization antenna using metamaterial, chiral metamaterial, and based on CMA by studying the moderating coefficient and by studying also separately the dipole and the chiral metamaterial using the intermodal coupling, we can show that there is a energy compensation between the electric and magnetic energy, and the chiral metamaterial could be a good candidate to design CP antennas. Thank you for your attention.
Thank you, Nadia, for this presentation. Are there any questions?
So I was wondering, how do you calculate the intermodal coupling coefficient? I was a little bit confused in terms of what is the X in your formula?
Okay. Sorry, I'll try to share my screen. So the X represents the reactance part of impedance matrix, and I represent the characteristic current. And yeah, so it's the relation between the characteristic current and the reactance part of the impedance matrix.
Okay, is this X the reactance of the entire structure consisting of both antenna and your metamaterial structure, or is just X for one part?
No, for the proposed structure.
It's for both structure. Okay, then isn't all the current supposed to be orthogonal? So,
sorry?
Then aren't the the currents between different modes, aren't them supposed to be orthogonal?
Sorry, I didn't get the question.
Orthogonal. Aren't they supposed to be orthogonal?
Like when I is not equal to J, aren't M, I, J supposed to be 0?
Yeah, I and J, they are different. Should be different.
Okay. No. My question is, like, if I is different from J, then isn't your numerator supposed to be 0?
No, when we have I different to J, we don't have 0. So we don't have, for example, intermodal coupling of mode 1 of mode 1. We don't have it. So coupling between mode 1 and mode 2.
Oh, your X prime is the derivative, right? Is it derivative?
Yeah.
Oh, okay, I see.
Mm-hmm.
Thank you.
You're welcome.
So thank you everyone, and probably a special thanks to the speakers during the presentations and for being there. And then also to all of you, because we have been running a little late. I saw that we have been losing a few participants on the way. We're really sorry for that. And next time you're trying to keep better track of the schedule and keep, to be on time.